Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have Robbie King, who will tell us about triply efficient shadow tomography. So my understanding is this efficiency has to do with basically how many samples you need and the runtime and sort of like how many copies you have to measure together. So that's the three things. So Robbie is a PhD student in Caltech supervised by Thomas Vidic. In your website, it says your third year. I don't know if that's updated information.
That's true. Yep.
Oh, okay. I see. Yeah. And you also work part-time at the Google Quantum AI. And he previously did his studies in University of Cambridge in math, I think. Yeah. So, yeah. So thank you for accepting our invitation. And yes, the floor is yours.
Thanks so much for having me. And so what kind of time should I aim for? Is like, yeah, how long?
So usually we have the seminar for 1 hour. It's fine if it flows over a little bit, but yeah, so that would give you maybe roughly 40 minutes, 45, depending on whether you want to be interrupted with questions.
Yeah, feel free to interrupt me with questions, by the way. Yeah. I would love that because, yeah.
Yeah, okay.
Okay, so today I'll be talking about triply efficient shadow tomography, and this was work with Robin Kothari, Ryan Babish, and David Gossett. So let's jump in. So this is the outline. First, I'll give an introduction of what we mean by shadow tomography and triply efficient shadow tomography. I will then say what are the new results that we achieve, and then we'll go through some of the key methods that enable these results. So what is shadow tomography? Shadow tomography is not a protocol, and it's not the same thing as classical shadows, which often people think. It's actually a task. So it's an abstraction of a task that sort of appears quite often in quantum simulation or physics, or ideas in quantum computing. So what is the setting? We are given access to copies of an unknown quantum state row, and these could come from, an experiment that you do in some physical setting, or they could come from, in the future, a quantum algorithm that you run on your digital quantum computer. And this might be some, many-body, highly entangled state, and we'd like to learn a series of features about the state, which often you can represent as a list of expectation values. So that's what we have on the right. We have O sub 1 up to O sub m. So we have capital M many observables that we would like to measure. And the task is to consume copies of the unknown state and to output these estimates, each to precision epsilon. So a question you can ask is how many copies of the quantum state are necessary to achieve this? And obviously, so, maybe these quantum states are expensive to produce, so we would like to minimize the number of copies that we need. So what are some observables that one could be interested in different settings? So if your state is representing some state on a series of spins, so for example, this is the standard setting of n-qubits, then the most natural set of observables is the k-local Paulis. So for example, x1 times y2 would be a 2-local Pauli, and you could be interested in measuring all of these Paulis to precision epsilon, and this would tell you useful information about the correlation functions, etc., in the state. Alternatively, suppose that your state is representing a fermionic state, perhaps encoded on your quantum computer via Jordan-Wigner, etc., or of course, always it could be in some physical experiment. Then the operators that we care about are no longer the k-local Paulis. They're instead these Majorana operators, which I'll define later, which sort of are the analog of local spin operators, but instead they're local fermionic operators. But they have, we'll see that they have some different features which are very important in, the shadow tomography task. And then the third example, which I'll include, is perhaps we have an n-qubit state and we would like to learn all of the expectation values of all of the Paulis. So there's, 4 to the n many Paulis. And, this is another example to keep in mind, which is quite informative. Now, I'll note at this point that the Majoranas, which I haven't defined yet, can be written as Pauli operators via this thing called the Jordan-Wigner transform, which we'll have a look at later. But just to sort of tell you that, in fact, it does fit into this framework of all of these examples are subsets of the Pauli operators. Okay, so this is in words what we said on the first slide, which is that the shadow tomography task is defined as given copies of an unknown quantum state, you want to estimate all of these list of expectation values to precision epsilon. Okay, so how could you perform this task? Well, suppose I had one observable. If I wanted to measure one observable, then to precision epsilon, then I should take 1 over epsilon squared many samples, and then the empirical average will be within epsilon. So one thing I could always do is I could always do one at a time. And this would consume linear in m samples. This would be m over epsilon squared if I took a new batch of samples for every observable that I'm interested in. However, this is could be very bad if m is large. So the question is, can we do better than this one at a time naive approach? So miraculously, Scott Aronson in 2017, who introduced this shadow tomography task, showed that this, in principle, can be exponentially improved. So he showed that we can solve this task in general using only log m many samples, which, this result is sort of hard to believe when you first see it. And it was a sort of heroic, crazy algorithm that he devised using these, gentle measurements, etc. But at least it is possible to do this. But so why doesn't this solve everything? And the reason it doesn't is because there are two major caveats to Scott Aronson's original shadow tomography procedure. The first is that the time complexity of his protocol is explicitly exponential time. So you have to manipulate these 2 to the n by 2 to the n density matrices, in classical processing, which we want to avoid. And the second caveat is that his protocol involves taking all of your copies of the quantum state and doing an operation which is entangling on all of them. And the reason why that is an issue is because we can imagine, suppose rho is on 100 qubits, right? And so in order to store that many copies of the state in quantum memory on a quantum computer, you would need 100 times 1 over epsilon squared many qubits, which could be, 1,000,000. So we don't, in order to make this protocol fit onto a small quantum computer, this is a major caveat, which makes it not practical even in the fault tolerant regime. This would be an issue. Okay. So this brings us to our definition of triply efficient shadow tomography. So we would like to maintain this logarithmic in m scaling of the sample complexity, which was exponentially improved from the one at a time approach. But we would also like the time complexity to be polynomial in n and m. Note that the time complexity has to be at least linear in m because the output of the problem is a list of m expectation values. So it's impossible to sort of have time complexity log m. But the way to think about it is that this is a sort of classical processing cost. And really the expensive resource is the copies of the quantum state, which perhaps you need to run a quantum algorithm to generate them, or to run some physical experiment and spend some energy. And we would also, the third requirement is that the measurements we perform we would like them to only measure a few copies at a time. So we don't have this situation where we need, a huge overhead in the size of our quantum memory. So, and in fact, we'll see that all of the measurements that we present will just measure at most 2 copies at a time. And in fact, this is optimal because we will also see that measuring 1 copy at a time is not sufficient for some of these tasks. But if you just measure 2 copies at a time, then you can suddenly achieve these tasks. Okay, so with the introduction out of the way, I'll go into what are our results. I guess I should, I'll pause for questions maybe, if there are any.
I have sort of a naive question. Like if I pretend that I only have like naive idea of tomography, so I would expect that you would need like many copies. Like if I wanted to, let's say, know the density operator, then you would need to have some parameters of the density matrix you need to estimate.
That's right.
So I just wanted to get like some intuition why, okay, here in this case, it's actually possible to do this even. Is there some simple intuition behind it?
Right, so that's a great question. And so the shadow tomography task is much easier than full state tomography. Because, so if you have to do full state tomography, you would need a number of copies that scales like the dimension of Hilbert space, maybe even the dimension squared of Hilbert space, I think. So, this is a lot. This is like 2 to the n. We haven't, this is much more than these, what we're trying to achieve here. But the reason is that is a much stronger notion of tomography. If you have the density matrix, then in fact, you can predict any observable, right? And there are actually, if you draw like an epsilon net over all of the observables, there's doubly exponentially many. So, this is a much sort of less demanding task where we only have, a list of observables and we want to know what those are. And this does not tell us what the density matrix is. Even if I know all the Paulis, it does not tell me the density matrix because the error is different, right? If I sort of, I just need each one to precision epsilon. There's no sort of notion of trace distance or, yeah, it's like an infinity norm sort of requirement, if that helps.
Okay, I see. Okay, thanks.
Sorry.
I don't know if... Yeah, go ahead.
Okay. Sorry. I just want to clarify. So this slide is your result, right? So.
No, we will not achieve this for general observables. We'll see that we'll go back to the examples that we gave earlier and look at those ones. This is still open how to do this in general. Yeah.
Okay. And so in your case, you mentioned the triply efficient is kind of, you can have efficient for all the 3 requirements: sample, time complexity, and measurement. But is there any constraint on the measurement? For example, it must be like a fully for Clifford measurement, or it can be restricted to Pauli measurement, or and is it required?
Right. We'll actually see that all of the measurements we perform are Clifford. In fact, Clifford and at most 2 copies. But we didn't. This is not a requirement. I guess you would like the measurements to be, efficient to implement. Right. You shouldn't try and do something that is like, some crazy measurement. But yeah, in fact, all of the measurements we'll see are Clifford measurements.
So if you are doing just few copies, so it means the result you get is not exact in some sense. It doesn't require. Can there be any noise in the measurement considered?
Yeah, I'm not sure. We haven't thought about that in particular, about the measurements being noisy. Yeah, it's a good question.
Okay, I see. Okay, thank you.
Okay, so what are the results? So this is what the landscape looked like before for these 3 examples that I gave earlier, which is, the spin operators, the fermionic operators, and all of the Paulis. So you can ask what is possible when you measure one copy of the state at a time. And this is the setting of classical shadows, which people often sort of conflate with shadow tomography. But if there's anything that you should take away, is that they are very different things. And classical shadows is a particular approach to shadow tomography where you measure one copy at a time, and it works well when the observables satisfy one of two conditions. Either they are local, for example, the k-local Paulis, or they are low rank. So in the case of k-local Paulis, this classical shadows protocol achieves triply efficient shadow tomography, and the sample complexity is log n over epsilon squared with a factor of 3 to the k, where k is the locality. On the other hand, if you want to do shadow tomography on all of the n-qubit Paulis, it was actually shown in 2021 that if you want to measure only one copy at a time, it's impossible information theoretically to have a good sample complexity. So the sample complexity must be exponential, which is not logarithmic in 4 to the n. So and this is sort of not too unintuitive when you think about it, because the Paulis are very non-commuting. So what basis would I measure in to try and measure a lot of them efficiently, right? There's sort of exponentially many different bases I need to pick in order to capture all of the Paulis if I'm measuring one copy at a time. But this result is actually much stronger. It says that even if I adaptively pick my measurements based on previous outcomes, still the sample complexity is necessarily exponential. So it's a very nice result. Okay. So the first thing we can do is we can show a similar theorem for the case of the local fermionic operators. So we can show that single copies, in fact, is not sufficient in order to get this log n scaling. By the way, I should mention that how many k local Paulis are there? So m here is n to the k in the first two cases, and in the last case, it's 4 to the n. So you have to sort of shift how you judge these sample complexities by how many observables we're trying to output. So for the case of the local fermionic operators, the sample complexity must be n to the k over epsilon squared if we measure one copy of the state at a time. So this is a lower bound. What if we now allow access to measurements on two copies? So for example, row tensor row. For example, you could do Bell sampling from row tensor row. This will be the key subroutine which lets us get around these bounds. Oh, by the way, I should mention this lower bound involves these Lavache theta function and Johnson graph techniques, which I think are sort of very interesting mathematically from these papers. So you can check it out. But okay, so what is possible with two copies? Well, we can now say that this allows us to achieve triply efficient shadow tomography already. So we achieve these exponentially improved sample complexities on these two cases where single copy measurements are provably, not sufficient. Okay. Right. So why are two copy measurements so powerful? How do they help us so much? Feel free to jump in with questions, by the way, anybody at any point. Okay. Okay, so the key is to use this Bell sampling subroutine. So what is the insight? The insight is that what is difficult about measuring all of the Paulis? Well, what's difficult is that they don't commute, so it's hard to pick a basis which simultaneously diagonalizes a lot of Paulis at the same time. So that's the problem. But the key is to realize that when they don't commute, they anti-commute, right? If I braid two Paulis, I either get a plus sign or a minus sign in the case that they don't commute. So what this means is that if I have two Paulis, P and Q, then the operator on two registers, P tensor P, always commutes with Q tensor Q because I braid the first two and I get a minus sign, and this cancels with the minus sign from the second one. Another way to say this is just, X tensor X commutes with Z tensor Z. So this is kind of interesting. And what you realize is that on two registers, there must be a basis which simultaneously diagonalizes all of the operators P tensor P. And it turns out that this basis is the Bell basis. So I have, qubits 1 and 1 prime in the Bell basis, 2 and 2 prime, so on. And this is the simultaneous eigenbasis of all of operators P tensor P. So what I can then do is I can put two copies of my quantum state on these two registers. So I have rho and rho, and then I perform these Bell samples. And this simultaneously gives us information about all of the expectation values trace of P tensor P times rho tensor rho, which is equal to trace of P rho squared. So, I can do a very small amount, like a logarithmic number of Bell samples, and this will tell me trace of P rho squared for all of the Pauli's P. And of course, you can square root this estimate to get an estimate for the magnitude of trace of P rho. However, we somehow lose the sign information. So we'll come back to this is a major sort of problem that we have to fix. And yeah, just to note at this point, if trace of P rho, if the magnitude is less than epsilon, we can output 0 for that Pauli, and that's a valid, estimate that's within epsilon of trace of P rho. So we sort of achieve the task for all of the ones that are small. So what's left to do is to resolve the signs of the Paulis who have large expectation value. And then we will sort of complete the task. So that is what that's the topic of the rest of the talk, is to how to resolve these signs. But this is the key sort of step that lets you get around these single copy measurements. And of course, it's not our idea. It's been around for a long time. But yeah. So the rest of the talk would be about how do we resolve these signs and then complete the task for various sets of Paulis. Oh yeah, I should say that this paper by Huang, Kuo, and Preskel also has a way of resolving these signs, but it is not triply efficient in the sense that it involves highly entangled measurements on many copies. So that's sort of the main dimension that we need to improve in our work. Okay, so the first the first way that we can resolve the signs is by using a technique that we call the mimicking state technique. So let's see what happens here. So by the way, I should pause for questions here actually, because this is a key sort of it's key to understand this part. So
okay, I just wanted to see. So this kind of like Bell sampling works. Okay, is it correct to say sort of because of the anti-commuting property of the Pauli?
Right.
Okay. So it should carry over to any other such kind of observable.
Right.
So, okay, but I don't really know any other observable that commute
yes.
and anti-commute. Okay.
Yes.
I was wondering whether there was like some other sort of non-trivial.
Yeah, we have another example in a different paper actually to do with these bosonic operators, which are like the Heisenberg-Weyl operators, or optical. People call them the displacement operators. These also have this property, and they're it's a different story where when you braid them, you get a complex conjugate, and then you get a phase. So you actually need the complex conjugate operator in order to make them commute. So you need the complex conjugate state in order to do the shadow tomography on those ones. So that's a different work that we have.
Okay.
But I think that is the most general example, actually.
It still works.
It does. The same trick still works. Yeah. Yeah.
Okay. Yeah. Okay. That was what I wanted to ask. Thanks.
So I want to ask in the Bell sampling, so you do the measurement according to the Pauli operator you already know in advance, right? So you must specify the Pauli operator you are interested, and then you do.
Not at all. We do Bell samples, and then you can come along with any Pauli, and I can look at my Bell samples and tell you what is trace of P rho from those Bell samples.
So when you do the Bell sampling, do you mean you have to do the? I'm not familiar with the Bell sampling. What you mentioned here, it means that you have to do for all the qubit at the same time, as you said, the Clifford measurement.
Yeah,
right.
One Bell sample is like I rotate every pair into the Bell basis, and I take a sample. So I get two n bits. I get sort of n bits and n bits. So each Bell sample is like two n bits, and I do this many times. And this is sufficient to get estimates of the magnitude of trace of P rho for any P. And there are exponentially many P, but this is a very small data set. So it's sort of, yeah.
Okay, I see. Okay, thank you.
Yeah. Okay, so how do we resolve the signs using the mimicking state? So what is this mimicking state? It is a state sigma that is large on the same Paulis that the unknown state is large on. So we can sort of first do Bell sampling, get the list of expectation values, and figure out where on which Paulis is our state large, and then we search for a state sigma that is also large on those Paulis. And such a state must exist because maybe there's only one, so maybe we find rho, or maybe there's multiple options, but it must exist because rho satisfies this property. So we will find at least one state sigma that has this property. We can then imagine preparing the state sigma on a quantum computer, and then Bell sampling from rho tensor sigma. And this will then give us estimates of trace of P tensor P times rho tensor sigma, which is trace of P rho times trace of P sigma. And we crucially chose sigma so that trace of P sigma is larger than epsilon. So that means we can divide through this by this equation by trace of P sigma to get trace of P rho. So this is the idea. And in order to find this mimicking state sigma, we can use this matrix multiplicative weights algorithm, which was also appears in the Scott Aronson's original shadow tomography. So this idea allows us to say that there is a triply efficient shadow tomography scheme for the case where the set of observables is the set of all Paulis. The reason it doesn't solve everything is because finding the state sigma is quite expensive. It's actually exponential time. So we allow exponential time when we're trying to estimate the set of all Paulis because there's exponentially many. But if we were looking at the sort of local fermionic operators, we want something much more efficient because there's only, say, n to the 4 of those. So we don't want to spend exponential classical runtime. So that's why this mimicking state idea solves this task, but not the local fermionic observables, which will be the topic of the rest of the talk. Okay, so how are we going to perform that task? Well, we use a different idea. So this mimicking a state idea is nice, but we'd like something that's more computationally efficient. Okay, so the key insight is that we can use coloring. So the first thing that we'll do is we'll build an object which we call the commutation graph. So suppose we have a list of Paulis. To build this graph, we assign a vertex in the graph to each Pauli, and then we draw an edge between any two Paulis which anti-commute. So you can see an example here on the right. We have a series of 2-qubit Paulis. I guess we have 7 of them, and all of these edges are when the operators anti-commute. Now, suppose I were to color this graph. So each color is an independent set. So there are no edges between vertices of the same color. So if you look at a color, each color is a mutually commuting set of Paulis. So I can simultaneously measure any independent set in this graph or any color. So you can see that once I have a coloring of this kind, the sample complexity to learn all of these Paulis scales like the number of colors in my coloring, because I can measure one color at a time, because I can simultaneously diagonalize those via some Clifford operation. So yeah, this object will be very, very important. Okay. So we can actually generalize this notion slightly and have a sort of randomized coloring. So this is, in graph theory, they call them fractional colorings, because it's sort of a integer program style relaxation of the notion of coloring. And then how do you define the number of colors? Instead, we say we have a distribution over independent sets such that the probability that any Pauli, so if I fix any Pauli, the probability that it appears in the random independent set is not too small. It's at least 1 over this chi. And if I have a regular coloring and I sample uniformly from the colors, this will be a fractional coloring with the same chi. So this also is enough to give a sample complexity that is linear in chi, because what we can do is we can sample from this distribution and then measure those Paulis in the simultaneous eigenbasis. Right. Okay, so something to note is that this classical shadows protocol, which people might be familiar with, where you pick a random Pauli basis for each qubit, this can actually be seen as an example of this formalism. So when I pick a random x, y, and z for each qubit, this is implicitly defining an independent set on the set of all Paulis, because it's saying which Paulis, which Paulis are in, diagonalized by this basis, right? So, for example, the first one here, we have x, y, z, z, y, x, x, y. So any Pauli which is, consists of these ones, so like x tensor, y tensor, identity everywhere else, for example, this one will appear in the independent set. So this is a particular way to get a fractional coloring. And the key statement of this version of classical shadows can be seen as saying that if I take the graph of k-local Paulis and I perform this fractional coloring, then the number of colors chi is 3 to the k. And you can see that because what is the probability if I have a k-local Pauli that I hit this basis on all of these qubits? It's like 1 over 3 times 1 over 3 times 1 over 3 for however many is the locality. So that's where this 3 to the k factor in classical shadows comes from. Okay, so now I will reveal what is our proposed strategy for how to perform shadow tomography on the Majorana operators, but also I think this is a good strategy for any sort of highly non-commuting set of Paulis. So first we do this Bell sampling step, and this lets us estimate the magnitudes of all of the trace of P rho. So then if, for all of the P such that trace of P rho is smaller than epsilon, we can safely output 0 as our estimate. And we have to resolve the signs of the ones that remain, which have magnitude larger than epsilon. So in the meantime, we build this commutation graph, which consists of all of the Paulis at the beginning. And then once we've done the Bell samples, we can throw away from the graph all of the vertices corresponding to nodes that we output 0 for, because they have small expectation value. And what we get is a subgraph of this graph, consisting of the Paulis that have large expectation value. And the key insight is that this graph, now we can expect it will have a good coloring. So we then, try and color this graph with as few colors as possible, and then we perform a Clifford measurement for every color, and that completes the protocol. So why does this operation of throwing away the small Paulis guarantee that there's a good coloring? Well, oh yeah, I should say that this idea was actually proposed in the original paper, which introduced this Pauli shadow tomography. But our contribution is to sort of formalize what this means. Like they sort of wrote 2 sentences about it. We sort of formalize how it should work, and also prove that in certain cases it works well in the worst case. So we sort of provide some evidence that it's a good. They propose it as a heuristic, but actually it does actually work in the worst case. Okay, so why should this guarantee a good coloring? Well, the intuition comes from Heisenberg's uncertainty principle. So the insight is that this graph of Pauli's that are simultaneously large on a quantum state cannot be too anti-commuting. It cannot have too many edges. And the reason that is because if it were anti-commuting, then Heisenberg's uncertainty principle would forbid all of these Pauli's being simultaneously large on a quantum state. For example, I cannot be simultaneously in the eigenbasis, for example, of anti-commuting operators. So this intuition sort of carries over, and you can show that. So for example, the first lemma that one can show is that this graph has no cliques larger than 1/epsilon squared. So before we do this throwing away, it could have large cliques that scale like with n. But after we throw away the small Pauli's, suddenly all of those large cliques disappear, and we only have cliques that are constant size, right? 1/epsilon squared, independent of n. And the idea of how you prove this is that you can use this inequality, which this looks sort of strange, but actually it's quite familiar, because what it's saying is that if I have a collection of mutually anti-commuting Pauli's, then trace of p rho squared the sum over trace of p rho squared cannot exceed 1. And this is a generalization of this block sphere constraint that x, y, and z all mutually anti-commute. And so x squared plus y squared plus z squared, the maximum value that can achieve is 1, and this is why we have a sort of block sphere for a qubit. So this is sort of a generalization of this idea, and this directly shows that we cannot have cliques, because a clique is a mutually anti-commuting set of values. Okay, so we know that this graph does not have big cliques, so at least we can hope that there will be a good coloring, because if there's a large clique, then you're sort of doomed from the start. But the clique number is actually independent of system size, so we can even hope for a coloring whose number of scales independent of system size, which would be great. So if you have a large clique, then you definitely do not have a good coloring. But is the opposite true? Like if you have no large cliques, then there is a good coloring? And it turns out that is not true in general. You can have graphs which are counterexamples to this. But in graph theory, they sort of studied this question, and they came up with this notion of chi-bounded, which is a set of graphs where it is true that a small clique number guarantees a good coloring. So this is not true for all graphs, but this is what this chi-bounded refers to. Okay, so I'll briefly pause here to see if there are any questions again.
So I'm not quite sure, how do you make the graph? The graph is determined by the Pauli observable you are interested, or is determined how to, if the graph correspondence according to which principle you are using?
Yeah, so you just you have your list of Pauli's, and you build the graph by just saying, okay, which one's anti-commute, and if they anti-commute, then I draw an edge between those two nodes. So I can perform operations that are take polynomial time in the number of Pauli's. That's okay. So I can build this. The graph is not too big. I can sort of just explicitly write down the adjacency matrix.
So once you have the Pauli observable, you can have a algorithm to have the graph correspondingly, and then with the graph you can already know how's the chi is bounded according to the graph, so that you can determine all the stuff.
Well, you need so it's easy to create a graph, but then it's not easy in general to find the best coloring. That's sort of a NP-hard problem. So you need an algorithm that's going to produce the coloring, and then you need to show that this algorithm, or believe that this algorithm is going to work well. So yeah, finding a coloring is not an efficient thing always, but you can have graph coloring algorithms. Yeah.
I see. Okay, thank you.
So I might just grab some. I'll be right back and grab some water. Okay. Okay. So next we'll see.
I just have a quick question.
Yeah.
So at least for the Paulis, is it easy to describe sort of like what subset of Paulis would have a chi-bounded graph?
Right. So I guess one way to say where we're going with this is that if you take the graph corresponding to the local Majorana operators, this is a chi-bounded set of graphs. That's sort of the result.
Mm-hmm.
Yeah. And I don't know about the case of all Paulis. In fact, that's an interesting open question. Yeah.
Yeah. All right. Thanks.
Okay. So next we'll talk about what are these. Sorry, I just spilled water. Next we'll talk about how can we apply this strategy to the case of the Majorana operators. So we need to see what those are now. Okay, so I think the best, or the quickest way to introduce what these operators are is just to say, what are the commutation relations that they satisfy. So it's given a fermionic system on n modes, you can write down 2n operators, and then the relevant set of observables are the ones that are low degree in these 2n Majorana, so-called Majorana operators, and they all mutually anti-commute. That's the key sort of property. So this is sort of a more general notion of what is a local operator than what you would have on like n spins, for example, and the k-local Paulis. And in fact, if you try to embed these into Paulis, it's impossible to do this in a way which makes them into local operators. But you can embed them into Paulis if you are okay with them having high locality. So the first example of this is the Jordan-Wigner embedding, which sort of creates these strings of Z's before, and then these you can check they have this correct commutation relation where they mutually anti-commute. And there's another embedding you can do based on a ternary tree from this 2019 paper, which sort of achieves that they are all log n locality, but still not constant. So here we can sort of identify each branch of the tree with like x, y, and z on a different qubit, and then to see what is the embedding of a leaf node, you sort of look at the Paulis that are in the path from the root to that node, and you can also check that these mutually anti-commute. Right, so I'm not telling you why these operators are important, but it turns out that they are in sort of quantum chemistry and fermionic physics and all of this stuff. All of the sort of physical properties that we would like to know are encoded by sort of degree 2 and degree 4 and degree 6, etc. Products of these Majorana operators. Okay, so a first example is we can look at the degree 2 Majorana operators. Now, in fact, you know what? Maybe I should skip forwards a bit if I should finish. Let's see. well, maybe I'll skip the last section. So I'll keep going here. So, so the first example we can look at is if we want to measure all of the degree 2 Majorana operators, and I should note that only the even degree ones are sort of physically relevant. So I could be interested in like C1, C2, and the fermionic people would call that a one body RDM, reduced density matrix. And then, or the degree 4 ones would be the sort of 2 RDM, the 2 body reduced density matrix, so on. But we never sort of have odd products. Yeah. So the degree 2 is the sort of lowest case. And here we can, so this is a bit confusing, but this graph was actually a different graph. It's the graph where the nodes are now single Majorana operators, and the edges correspond to the operators or Paulis that we want to learn. So I apologize for sort of throwing a different graph at you. I tried to make the nodes into squares, so it's clear that it's different. But the key reason why I'm introducing this different graph is it lets you see why that this throwing away procedure guarantees a good coloring in this simple case. So once we throw away the operators, once we do the Bell sampling, we throw away the operators that have small expectation value. What happens to this graph is that the degree becomes very small. So before the degree was n, right? It was a complete graph. We had all of these operators we wanted to know about, right? We wanted an expectation value for every edge. But after we do the throwing away, the degree goes from n down to 1 over epsilon squared. And the reason is because of this anti-commuting bound, right? So if I have the Majorana operators, which all touch the same vertex, this forms a mutually anti-commuting set of operators. So this bound tells us that we cannot have more than 1 over epsilon squared many touching the same vertex, which tells us that the degree is small. And if you have a graph with a small degree, now we're searching for an edge coloring, right? A coloring where because if you have 2 quadratic Majorana operators that don't touch on an edge, they actually commute. So an edge coloring is sort of the right object to sort of partition this into sets of commuting operators. And a low degree guarantees that there is a good edge coloring for the graph. And you can in fact find this edge coloring by, the greedy algorithm will actually sort of be good enough. So this sort of completes the steps and says that there is a triply efficient shadow tomography scheme for the case of degree 2 Majoranas. But how can we deal with higher degree? So right, so without going into too much detail, it's sort of a similar type of idea. So we're going to use the fact that there are no large cliques in this commutation graph, or there cannot be too many sort of mutually anti-commuting Paulis, and deduce from this that the graph should have a good coloring. And in fact, we give a coloring algorithm, and we show that this coloring algorithm will work. So this is the way in which we achieve a triply efficient shadow tomography scheme for the set of all degree k Majoranas for any constant k. Okay, so I could stop here, or I could go into the last section. What would be better?
I guess it just depends, like how long is this last section?
Let's see. 3 slides. It's only 3 slides. So, and I think it's interesting because it's like
yeah, I think it's fine. You can just finish. It's fine.
Okay.
Yeah.
So right. So we sort of completed all of the things we set out at the beginning, which is to get triply efficient shadow tomography schemes for the case of all Paulis and the case of any constant locality fermionic operators, using just 2 copy measurements. So we've seen all of that. So this last section is about sort of an interesting sort of question that arises from this investigation. So here is the theorem that we managed to show, which is sort of tangential to the results I was describing, but I think is nevertheless quite interesting. So suppose you have a quantum state rho, and you take the commutation graph of the Paulis that are large on this quantum state. So we can write this as G sub epsilon. And this is a graph that is corresponds to the state. So if I have a different state, I would have a different graph. So we were able to show that the this graph should have a fractional coloring of size n to the 1 over epsilon squared. Now, why is this not trivial? And the reason is because if I just have the graph of all Paulis, then I necessarily need 2 to the n colors in order to color the graph, which, as you'd expect from this sort of lower bound that tells you with single copy measurements, you need 2 to the n measurements. So, but this says that if I throw away the ones that are large on a quantum state, even if I started with the whole Pauli graph, then, for constant epsilon, this is polynomial on n. So it's actually gone from exponential on n down to polynomial. And the proof is that, this graph, the Pauli graph, it turns out has no long induced paths. And this is enough to guarantee this chi-binding property. So this allows us to do something quite, which seems quite counterintuitive and powerful. For example, what we can do is we can perform Bell sampling and then throw away the large Paulis and then color this graph, the graph of the resulting Paulis, which are large, using n to the 1 over epsilon squared many colors. And then using that many measurements, we can, we can measure one color at a time and then get another sort of set of measurements. Now, we've only made a polynomial, if epsilon is constant, we've only made a polynomial number of measurements in total. So we have a classical data set, which has size polynomial in n. But this classical data set, you could extract any Pauli expectation value, including the sign, to precision epsilon. So, we've sort of compressed our quantum state into a polynomial sized classical data set, which encodes the expectation values of any of the 4 to the n many Paulis. So we call this rapid retrieval Pauli compression. So you sort of can turn your state into a classical data set in this way. So I thought this was kind of, we thought this was interesting. But we actually conjecture that you can even do better than this. So I'm curious about whether or not this is true. I think that the coloring of this G sub epsilon graph, there's a chance that it's as small as 1 over epsilon squared, independent of n. So this would mean that once we throw away the Paulis that are large, sorry, I keep saying, once we throw away the Paulis that are small and only keep the large ones, then the coloring number goes from 2 to the n down to independent of n. It goes to 1 over epsilon squared. And in fact, I don't know of an example where this is not true. And, numerically, this seems to hold, etc. So this is the conjecture. And, if this was true, this would sort of suggest that we can do triply efficient shadow tomography for any set of Paulis, not just the Majorana operators or, it would sort of be, then we can do any sort of subset. But yeah, I'm very curious if, this holds or if there's a counterexample. And so I'll conclude my talk there. Thank you. Thank you so much.
Okay. Thank you very much for a very informative and very interesting talk. Okay, so I guess, so we're sort of like hitting the timing of the seminar, but we can still sort of try to take some few questions. So please, if you have questions, feel free to just unmute yourself and ask them now.
Hi, I actually have one question. So in your proof, you basically use 2 copy using bare basics as a handle to gain this efficiency. Would that efficiency amplified by going to higher copies, for example, 3 copies, GHZ states, and like K copies, for example?
Right. It's a good question, and I don't know if more copies can help in any way. Maybe they can, but I think it needs a new technique in order to exploit.
Okay.
Yeah.
Okay then. So one of our group members, Mingjian Hubert, he is very interested in this direction. So Mingjian, maybe you can think about this. Yeah.
Yeah, I think that's really exciting because this is sort of the only trick that we have is this Bell sampling one. So any other trick where you can exploit entangled measurements to do learning in a better way, anything like that is very interesting because this is a sort of new type of quantum advantage you can say because in experimental platforms, for example, you sort of prepare a quantum state and then you have to measure it straight away in some basis, right? But if you have a quantum memory and a quantum computer, you can sort of store one of the copies and wait for the next one, right? So if you're like sort of generating your states in a quantum computer, or you can imagine sort of transducing states from an environment, and if you have a quantum memory, this allows you to perform these entangled measurements on multiple copies. So I think searching for new primitives of this kind, I think is a great direction because I think it does lead to sort of new versions of quantum advantage, which are they're not sort of computational speedups, but they're sort of quantum memory learning advantages.
Yeah. I definitely agree because like for example, if the answer is yes, then there might be different representation of higher degree in like entanglement structures using representation theory, then that better represent the structure of the data, and then maybe you could improve from there. Yeah. Okay.
Yeah, and then
good.
and
Very
then it was
interesting.
impossible to achieve that data set sort of with just measuring one copy at a time in a conventional setting,
I see. Very interesting. Thank you for the feedback.
So you did mention that basically we have only this Bell sampling. So is it the case that even in 2 copies, I might even try to is there some other tricks that one can try to construct that would do maybe there's some cases where Bell sampling will not work, or is it known that Bell sampling is essentially the best thing to do with 2 copies?
Well, it only works with Pauli's, right? So
yeah, sure.
For example, I mean, I don't know. It's the only trick I know, and it's the only trick that I think the community knows. So any other tricks are sort of very would be very nice.
I guess I was just mentioning since then you don't even need to really jump into many copies right away. Even in the 2 copy case, there's still things that might be one can try to figure out.
Right. But yeah, you could imagine what kind of properties of the state you can ask the question, for example, what properties of the state are invisible to even 2 copy measurements that you can get by doing sort of a GHZ style 3 copy measurement. So maybe there's sort of certain properties that are sort of you need to go to higher and higher number of copies, maybe, right? But I would also say it's very dependent on the sort of properties you want to probe. So for example, if you want Pauli expectation values, then this Bell sampling works, but it doesn't work for anything else. For example, what if I have a set of observables that are like Pauli's but rotated by T gates, right? Even that we don't know how to do efficient shadow tomography.
See. Okay, cool. All right. I guess maybe there will be other people who have questions.
Thank you for the very nice and interesting talk. I'm looking for this direction, and I think the multi-copy is quite interesting. I definitely will go somewhere there. And actually, I have a question about, you mentioned that you are going to determine the sign of the expectation, but I don't quite follow that. How to determine the sign?
Right. So it's just once we have this coloring, we can just measure in the right basis, and we actually get more. We get the whole expectation value, including the sign, right? Like if I measure in the eigenbasis of an operator, that tells me what is the expectation value of the operator. So including the sign.
I see. And then when you mentioned about the absolute value in the middle, that's just help you to discard some small number.
Yeah, basically the only role of Bell sampling is kind of crazy. The only place we need it is to decide which Paulis are large, so we can focus on those, and then even that is enough to get around these sort of single copy lower bounds. Yeah.
Then once you determine which subset to discard, and you just focusing on the left part and start the coloring of the gray.
Yes.
Okay,
Yes.
I see. Okay, good. Thank you.
Yes.
Okay, all right. So I guess we can sort of end here. So thank you everyone for attending Robbie's talk. Yeah, so yeah, I'll also be ending the recording, and I'll maybe give you the link of the recording once it's ready. Yeah, so yeah, thank you again for, I think I learned
so much.
quite a bit, quite a bit about this stuff. Like it's not really the sort of thing I've been studying. Yes.
Okay, thank you so much for having me.
Bye bye. Bye bye.
Okay, thank you very much.